nanoHUB.org. Online simulation and more for nanotechnology.
Greetings, everyone. I'm Alejandro Strachan, Professor of Materials Engineering at Purdue University. And in this short presentation, I'm going to introduce SimTools, which is a new way of delivering simulations in nanoHUB. For those of you who are not familiar, nanoHUB is a cyber infrastructure supported by the US National Science Foundation that provides access on your web browser to a large number of simulation tools. Every year, we serve over 21,000 simulation users who come to the site and run online simulations using their web browsers, and over 2 million visitors every year come to nanoHUB for our educational content. So what nanoHUB seeks to do is connect tool developers with the end users of their products via cyber infrastructure. And our goal is to enable our users to innovate in research and in education through these products. And if you've been to the site, you will know that the way folks interact with these simulation codes and data tools is via easy-to-use online apps that look like an app on your phone, but under the hood, they run a powerful scientific code. We have science workflows with Jupyter and lots of data science and machine learning. What I'm going to tell you about is a new way of delivering simulations that we call SimTools, which has a modern design in terms of delivering the simulations and the data associated with those simulations. Many of you may be familiar with FAIR principles as they apply to data. There's quite a bit of interest in the scientific community to make the data that we generate findable, accessible, interoperable, and reusable, so as to speed up the innovation in research and speed up progress. So by findable, we mean that the data needs to have a unique identifier, has to be indexed and searchable. By accessible, it means that the data should be accessible through protocols that are open, that can be universally implemented. By interoperable, we mean that the data needs to use a formal language to describe, to represent what it contains and what it is. And reusable means that the data has to have metadata associated with it that tells within each application the context in which the data was obtained, so that others can assess whether that data can be reused for other applications. So there's a lot of work in making scientific data fair. And what's interesting is that these principles apply not just to the data, but in the case of computational science and engineering, the simulation tools and the associated workflows that are used to generate the data. And so I'm going to tell you about SimTools that addresses this need for fair simulation tools and workflows. If you're interested in learning more about FAIR principles, this is a cool paper. It's not very technical, and it describes the principles that I've discussed in a lot more detail. So I'd encourage you to go ahead to go and read this paper. So let me show the need for SimTools with an example of a research workflow, a relatively simple research workflow in my field, computational material science. So let's say I would like to calculate the melting temperature of a metallic alloy using molecular dynamics. The steps that I would take to do this, or my students would take to do this, are more or less the following. You first generate a structure. Let's say I'm interested in a high entropy alloy, and so I have to generate this structure randomly. Once I generate the structure, I need to decide on what model I'm going to use to describe how atoms interact with one another. That is called an interatomic potential. And maybe I go to OpenKim, that's an open repository of models, and I can select one from their list of published interatomic potentials. With that, I'm going to run my actual MD simulation. Maybe I use the code LAMPS from Sandia National Labs. And we're going to, without getting into all the details, the LAMPS produces a molecular dynamics trajectory where atoms move and where their positions are as a function of time, or what their velocities are as a function of time. And I need to actually do quite a bit of analysis before I can assess whether I can extract a melting temperature and what confidence I have in that melting temperature. So in this case, the analysis has to do with, for example, identifying that in my simulation cell I have both liquid and solid, that they're coexisting in equilibrium. And after that, I would compute the average kinetic energy from which I can obtain a temperature and the melting temperature. That's the process. So this is just an example, but I think it's representative of typical research workflows. They're complex, they involve multiple steps, and in practice, these steps are not fully described in publications. Actually, English is not the best language to describe this process. And when we do research, often we include ad hoc scripts, maybe manual steps, and all of these issues conspire into having workflows that are not findable, accessible, interoperable, or reusable. So they're not fair. And so the science that is generated is very hard to reproduce. So even in best case scenarios, when the authors are very careful in describing the steps in a publication, reproducing research results can take months, even by experts. So to address these issues, we designed SimTools with the goal of making simulation workflows fair. So if we extract the essence of a research workflow, there's a bunch of inputs that get processed, and it generates one or multiple outputs. And that's the actual final quantity of interest that I'd like to obtain, for example, melting temperature. So what we ask the tool developers to do when they write a SimTool is the following. They have to formally declare all the inputs and the outputs. These inputs are the ones that the users will be able to control. Then they need to implement every single step that to relate the inputs to generating the actual final output. And all of this is implemented in Jupyter notebooks that are very commonly used, widespread with widespread adoption. And as you will see, creating this SimTool is relatively simple. Now, nanoHUB, the SimTool library, does a lot of the magic that connects these to the users. So the SimTool library, when you register a tool, they're queryable, so anyone can find the tools and can find the inputs and the outputs of every tool. So the inputs and the outputs and the descriptions of the tools are all queryable. Inputs are verified before the simulation is launched, and this includes unit conversion. And outputs are checked after the workflow execution. So we make sure that every output that's declared is actually has a value in it. And every published SimTool has a DOI and are indexed by Web of Science and Google Scholar. So they can be found in multiple ways. Now, importantly, we also cache, we save automatically every single run of a SimTool that our users perform. And this cache is available and queryable so that if another user requests the same simulation we've already performed, we provide results instantaneously. And of course, this helps with reproducibility. And so our users can benefit from all of this infrastructure in accessing the SimTool. So let me show you an example of a SimTool and walk you through the steps required to create a SimTool, which are it's very simple. As I said, the first thing you need to do is declare all the inputs and all the outputs of the SimTool. And so there are different types of inputs and outputs, like text, real numbers, lists, even images. And each input and output has a description, so the users can understand what they are. They can have units, they can have options to select from, and you can see here units, the temperatures in Kelvin. So after you declare the inputs and the outputs, there's a step that's required, that's the parameterization. And that's done with paper mill. And this step is going to be used so that when a user calls a SimTool, the actual user-defined parameters are passed into the notebook. And after that, you just basically set up your simulation and execute. And here, you can access resources outside of nanoHUB. So you could launch a tool, a simulation in a HPC system, for example, and get the results and finish your job, or you can run the simulation locally. So once the simulation is actually done, and this of course can be one simulation or multiple simulations, you post-process the results, you do all the analysis that needs to be done, and you save your outputs. All the outputs that have been declared, you save them explicitly. And as I said, the SimTool library checks that all of these outputs have appropriate values. So that's what the developer needs to do. Let's see now from a user perspective how you interact with the SimTool. And as I'm going to show you, these are the details, computational details of how you need to interact with the SimTool. Users may interact with the SimTool in this way, or through, as I will show you, a simple graphical interface where all of this code can be hidden from the end users. Okay, but let's say you're familiar with Python and you'd like to interact with this SimTool. This is what you would do. All the users can explore all of the installed and published notebooks. You get a list of all the notebooks, including the descriptions. And so you can select the notebook, the SimTool that you're interested in. Once you select it, you can load it, and you can explore what the requirements and the services that this SimTool provides. So the requirements are, of course, the inputs that you need to provide, and the services are the outputs that this SimTool generates. So this is just exploring, not running anything, just understanding what the inputs and the outputs are. Once you're ready, you can parameterize the SimTool. And so in this example, we have to, for this melting temperature calculation, we have to provide an estimate of the initial values for the temperature of the system. And as I said, well, I don't think I said it, but numerical values have units or can have units, but also you can have ranges. So as a tool developer, you can say this input can only vary between 10 and 15 because those are physically meaningful results, values. So in this case, if your temperature that you try to input is 50,000 C, which is way outside of the reasonable temperatures for this class of materials, the SimTool will check the range and will not allow you to input that value. The other example that I want to mention is that unit conversion. So I can say, okay, the temperature is 1,000 C, and automatically the SimTool changes that value to Kelvin, which is what the SimTool wants to accept. And so this saves, as a tool developer, you can make sure that the values that the user's input make physical sense. Once you parameterize the tool, you just run it, okay, very, very easily. And you get a progress report of how much progress the execution of this notebook, a progress report during execution. And the last thing you do is once the simulation finishes, you read the outputs, you know what the outputs are, and you can explore every single output. Okay, you can get pictures and you can also get numbers. So in this case, we get the value of the predicted melting temperature, a confidence interval, and some results that indicate to the user whether how well converged that simulation is. If you're interested in exploring this SimTool, here's the link. You can go and run it for yourself. Since I've been talking about melting temperature calculations, I'm going to show you how the simulation actually works. You try to create a system where you have coexistence of a liquid and a solid sample, and you know that if a liquid and a solid are in coexistence, then at a given temperature and pressure, then that's the melting temperature, right? So you can see that the simulation at the top was too cold, and everything turned into a solid. The simulation at the bottom is too hot, everything is turning into a liquid, and the simulation in the middle, that temperature was the Goldilocks type of temperature where you have coexistence of the liquid and the solid, and from which you can obtain the melting temperature. And so the SimTool actually does this analysis, analyzes the fraction of the solid, the fraction of the liquid, and so it actually, with significant confidence, it can predict, it can tell the user whether it calculated the melting temperature or whether the simulation failed at calculating the melting temperature. Still provides all the details, but you as a user, you know that melting temperature cannot be trusted. The simulation, the input parameters were not appropriate to computing an actual melting temperature. And so let me show you some of the cool things you can do very easily once a SimTool is deployed. In this case, we perform high throughput simulations where we wrote a little workflow that called the SimTool multiple times, selecting different elements and selecting different models, different interatomic potentials from the OpenKim repository of models that I've mentioned earlier. And with just a few lines of code, we can automatically and reproducibly evaluate all of these models and assess which one performs well, which ones perform well in terms of predicting melting temperatures. So those dashed lines are the experimental melting temperatures. Another thing you can do that's very cool is you can drive one of these SimTools with a machine learning workflow. In this case, we're looking at high entropy alloys, and we're trying to find the alloy that maximizes we're trying to find the composition of the alloy with the highest possible melting temperature. And we use a technique called active learning to do that. And again, we have a workflow that calls the SimTool services to provide information. The other thing is SimTools can also be used to drive graphical user interfaces, apps. So this is an app, simulates a quantum dot. You can, here you're exploring graphically the wave function that results from a quantum dot. You can select different geometries of the dots and look at the eigenvalues and the shape of, you can see here changing the shape of the dot, and the wave function will also change. These are like artificial atoms. And the important thing for this presentation is that there's a SimTool underlying this app. However, as a user, you don't have to know anything about the SimTool, how you're interacting. You don't need to know anything about Python, but you can benefit from an app, for example, for education, to use in the classroom, or an app like this for research, where the users are domain experts, but they don't need to become computational experts. As a summary, we created SimTools to make scientific workflows fair, and I would say fair with a double R, because we're also, in the case of workflows, we're also interested in reproducibility. So we have end-to-end computational workflows that contributes to reproducibility. The published SimTools are containerized. That also helps with reproducibility. They all have DOIs and are indexed by Web of Science and Google Scholar, so they're findable and accessible. And you have to declare inputs and outputs that are validated. This also contributes to reproducibility and interoperability, because you know the requirements and the services of each SimTool. And the fact that these services are, including their metadata, including the descriptions, are queryable, makes them interoperable, findable, and accessible. And the fact that we have automatic result caching, so every time a user of a published tool runs an actual simulation, we automatically cache it. And then everyone else, every other user has access to this cache. That makes it accessible and reproducible and interoperable. So if you'd like to learn more about SimTools, here are some important links in terms of the actual documentation of SimTools. You can explore a very simple example of a SimTool in this link. And this is a tool that really doesn't do much, except that it exemplifies all of the actual inputs and lists and all of the actual outputs. So this is a good way to start, learn about the inputs and the outputs, and you can use this as a model to create your own SimTools. Once you created your SimTool, you can actually publish it in nanoHUB. So if you go to this link, you're going to learn the different options to do that and learn about the process of tool publication in nanoHUB. It's actually very simple. It's all automatic, kind of similar to publishing a paper, a little less onerous, I think. When you publish the tool, as I said, it's going to be indexed by Web of Science and Google Scholar. And the last link provides you a simple guide to using Jupyter in nanoHUB that you can use this environment to develop SimTools and other types of tools. Thank you very much.